All right, welcome back to another calculus lecture. So in today's lecture, what I want to talk about are some of the properties of the integral that we're going to use when we do computations with the integral. Most of these properties are going to come from either the fact that the integral is a limit, so some of the properties that we have about derivatives carry over to integrals because both of them are limits, and those properties are just being derived from that fact. Or there's sort of some geometric aspects of the integral that we can use to derive properties about the integral. Okay, so the first of these properties, we'll go ahead and just state these as theorems. So theorem. So the first theorem is that the integral is linear. And what I mean by that is let c be a real number. Then the integral from a to b of, and what I'll do is I'll do a linear combination of two functions. So I take my first function, I multiply it by this real number c, and then we'll add on another function. So this expression, the integral of c f of x plus g of x, this is equal to c times the integral from a to b of f of x dx plus the integral from a to b of g of x. Okay, so what this is saying is that if I have a scalar, this constant, this real number, I can actually just move this outside of the integral and compute my integral and then multiply by c later on. Similarly, I can take my function g of x and I can actually just split this integral up into a sum of two different integrals and compute it that way. So an example of this, we have that the integral from 0 to 2 of 3x squared plus x dx, this is equal to 3 times the integral from 0 to 2 of x squared dx plus the integral from 0 to 2 of x dx. And you can see that it's potentially much easier to sort of compute these individual integrals rather than sort of thinking about this whole integral with everything inside of it. The integral represents the area between the curve and the x-axis, and so being able to sort of break this up into these smaller integrals, it's typically easier, at least from a geometric standpoint, to analyze functions by themselves rather than sort of combinations of functions. This isn't always the case, but a lot of the times it turns out to be a little bit simpler to do the analysis this way. So all that to say, we can break integrals apart like this and do our computations like that. Okay? So that's our first theorem. The second theorem is more just, this is true of derivatives as well. The next one is really just true of integrals, and it's a notational thing. So so now we're going to let a be less than c be less than b. So these are going to be three real numbers such that c is in between a and b. So the first property that I'm going to list isn't going to use this fact, but the second one will. So 1, the integral from a to b of f of x dx, this is equal to, and sometimes it happens in applications that your limits of integration are sort of backwards. You have the bigger number in the bottom limit and the smaller number in the top limit. So if you ever need to reverse the direction of the integral, reverse the sort of order of these things, then all that happens is you pick up a negative sign. So this is b, integral from b to a now, of f of x dx. When you get into Calc 2, you'll do something called a change of variables, and actually we'll do that a little bit in this course as well. But sometimes when you change variables, you incur a negative sign, or your limits of integration get switched around. And so if you need to reverse the limits of integration, sort of swap them like this, the only thing that happens is you pick up a negative sign. Okay? Now the second property is that if I have an integral from a to c and then an integral from c to b of the same function, well, you might imagine that if I do the integral from a to b, then I should just get the sum of these two integrals. I should just do both of the integrals together. And in fact, that is exactly what happens. So the integral from a to b of f of x dx, this is equal to, and what I can do is I can split the integral apart into a to c of f of x dx plus the integral from c to b of f of x dx. And geometrically, what's happening here is, well, this is just the full area between the curve f of x and the x-axis between a and b, and then I just break it apart into each of the two pieces of that area, the part of which lies on a to c and the other part of which lies on c to b. And then I add them together and I should get the full area. So as an example of this, so let's say I have the, or maybe, do I have my, darn, I don't have my ruler in here, alas. Yep, nowhere near. So if I have the, let's just draw a function right here real quick. I have some function f of x. Here's a, here's b, and then I put another point in here, c, in between. Well, you can see that if I wanted to compute the area under the curve between a and b, well, then that's really just the sum of these two individual areas. Well, that's exactly what this expression is saying. It's that the integral, this whole area, is equal to the sum of these individual areas. Okay? Nothing mysterious happening there. Oftentimes, if you're doing a specific problem, a point C might be some sort of point of interest. It's where functions are intersecting, or you have a zero of a function, or a critical point, or something like this. And you may want to split the integral at that point just to be able to analyze it better. And this shows you that you can, in fact, do that. Okay, and we could have the areas being negative. They could sort of switch around. This remains true. It doesn't matter that we just have positive area right here. We can actually do this no matter what. Okay, so that's the other sort of properties of the integral. The next properties that I want to talk about are maybe less, they sort of come up less often, but are no less important. So I guess before this, let me make a quick definition. So this next theorem pertains to even and odd functions. So before we talk about even and odd functions, let's sort of define what they mean. So a function f of x is even if f of negative x is equal to f of x. And f of x is odd if f of negative x equals negative f of x. Okay, so these are the rigorous definitions. Let's maybe look graphically at what this represents. So example, doing a lot of examples today. So if I have, let's just, oh, whoops, let's actually not do that. So let's put axis here and an axis here. So two very sort of familiar examples of even and odd functions are the sine and cosine functions. So the cosine function is an even function. So if I were to draw that, then it would look something like this. And you can see that an even function is going to be symmetric about the y-axis. So if I take and evaluate f at a negative value, it's the same as evaluating it at a positive value. So here you can think of x as a positive number. And so if I evaluate x at a positive number here, it's the same thing as evaluating it at its negative counterpart over here. You get the same thing on either side. Similarly, so this is like f of x even, cosine of x is an example. Similarly, for an odd function, what you have is that if I evaluate it in the positive side over here, then what happens is I negate it over when I evaluate it on its negative counterpart. So if I plug in a positive x value and I get a positive value, then when I plug in the negative of that value, I simply negate my function value and I get the negative version of that number. Okay? So this is f of x odd. And sine of x is an example. Other examples of even functions are polynomials polynomials where all the exponents are of even degree. It doesn't matter if you put in a positive or negative number, you get the same thing out on each side. Odd functions, anything where you have a polynomial with odd exponents. You put a negative number in, you get the negative that factors out of everything. That's sort of where the names of these come from. If you have even powers, you have an even function. If you have odd powers, you have an odd function. It is possible for a function to be neither even nor odd. This is not an exclusive classification of all functions, just a property that some functions happen to possess. So if a function happens to possess the property that it's even or odd, then some of its integrals, the integral of this function over certain intervals, can be computed in, you sort of get shortcuts for computing them. So we'll go ahead and write down the theorem for that. So theorem, and actually we'll just do this as a numbered thing. So if f of x is even, then the integral from any negative value to its positive counterpart of f of x dx. Well, we can sort of look at the graph here. Imagine that a is a positive number, and the integral from 0 to a, if I just sort of imagine it only like this, then the integral from 0 to a is going to be the same as the integral from negative a to 0, right? And so the integral over a symmetric interval like this is just going to be 2 times the integral from 0 to a of f of x dx. Because when I put in a negative value for x, I can just rewrite the integral with the positive value using this equality for even functions. Okay? Similarly, if f of x is odd, f of x is odd, then the integral from negative a to a of f of x dx, well, here we have something even nicer happening, because notice what we have. We have, if I am looking at sort of this area over here, it's, if I imagine a as like before I get to this 0, the area is positive, but then if I flip over here, the area is going to be negative. And because of the symmetry of the function, the areas will actually just cancel each other out. And so the integral of an odd function over a symmetric interval like this is 0. You actually can just evaluate it very quickly like that. Okay? So as an example of this, we'll just go ahead and use the two functions that we have up here. So we have that the integral from negative pi to pi of cosine of x dx. This is equal to 2 times the integral from 0 to pi of cosine of x dx. And the integral from negative pi to pi of sine of x dx. This is equal to 0. Okay, and you can look at the graphs of the functions to sort of convince yourself of this fact. Okay, this is exactly the graph of cosine, this is the graph of sine. Well, not exactly, because I'm not very good at drawing things myself. But when you have integrals over a symmetric interval centered around 0 and you have an even or odd function, you can use a few shortcuts to kind of evaluate these integrals. Okay? So the last thing that I want to talk about is it doesn't pertain to actually evaluating the integrals, but rather estimating them. Sometimes in applications, you actually can't evaluate the integral explicitly, and so you need to somehow give upper and lower bounds for it. Say, okay, well, I can't compute it exactly, but maybe I can give some indication of how big it is. Okay, and our next theorem addresses that. And this is the comparison theorem for integrals, or at least a version of it. So theorem, a lot of theorems today, not a ton of hard and fast calculations. So let m, little m, be less than or equal to f of x, be less than or equal to capital M on the integral or interval from a to b. It's really easy to mix those words up. Sorry if I've done that in previous videos. So f of x here is bounded below by some number m and bounded above by some number capital M. Well, if f of x is bounded by these, well, you might imagine that if I integrate f of x over some interval, if I think about areas, then I can bound it below by something depending on m and bounded above by something depending on capital M. And indeed, this is the case. So then, the integral, I'll write this in the middle of the page here, from a to b of f of x dx is less than or equal to, and I'll go ahead and write out the inequalities and then finish this theorem, and then we'll talk graphically about why this is true. So the integral of f of x dx, well, it's less than or equal to, well, let's just insert the bound for m right here at f of x dx. This is less than or equal to the integral from a to b of m times dx. M is just a number, so it comes outside the integral. And then what is the integral from a to b of dx? Well, it's the integral of like 1 dx, which is just the horizontal line, which is at y equals 1. And so the integral is just going to give you the area of that beneath that curve with the x-axis. Well, you have a rectangle then of width, b minus a, the width of this interval, and height equal to 1. And that was a verbal description, but we'll draw a picture in a moment. So this is equal to m times b minus a. And then likewise over here, we have little m times b minus a. Okay? So all we're doing is just bounding the area here of f of x by two different things. And we'll draw a picture of that in a moment. So now for the second part of this theorem, so now suppose that f of x is less than or equal to g of x on a to b for some function g of x. I don't know exactly what it is. I don't know what f or g is, but suppose I have two functions that satisfy this. Then, well, sort of you can sort of think about the same thing happening here. The integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. The integral sort of is able to see this inequality and preserve it after the process of integration. Okay, so let's talk a little bit geometrically about what this represents. So example. So this first inequality, so suppose 2 is less than or equal to f of x, which is less than or equal to 4. So we have some function which is bounded above and below by 2 and 4, respectively, or reverse that, respectively. Anyways, you get the point. An example is, and graphically we can draw this very quickly. So here's, A, here's B, here's 2, here's 4, and then my function does something like this. Okay? So it's bounded above or bounded below by 2 and bounded above by 4 in this interval. You know, it may do something else over here and here, but at least in this interval, we have this bound. Well, let's think about what the integral is. Well, the integral is just this whole sort of area. I'm trying to do this very lightly, but it's a gel pen, so that doesn't exist with the sort of colors here. So the integral of from a to b of f of x is just capturing this area right here. Well, let's think about what each of these quantities are. Little m times b minus a is just the area of the rectangle that has height equal to little m, which is 2 here, and the width is just the width of this interval, b minus a. So if I have 2, and then we'll use a different color for 4. I should have done this to begin with, but then what I have is, here's my rectangle, and then my bigger rectangle. So here's my green rectangle, which is my lower bound for the area. You can see that the area is smaller than the area below the curve between f and the x-axis. And then the upper bound is just this bigger rectangle. It's the height, big M, this 4, times the width of this interval. Okay? And so the area of this pink rectangle is larger than the integral of f of x, this area underneath this curve, and that in turn is larger than the area of this green rectangle, which is you know, just this lower bound right here. So sometimes you have functions where it's sort of very difficult or even impossible to calculate their integral, but nevertheless you can give some sort of estimate for the size of the integral using this method. Okay, and same thing happens for this second guy right here. So if I have you know, another function, another interval, a to b, here's f of x, and then here's g of x, then you can see that the area, the green area here, is bigger than the purple area. There's just more of it, okay? And so the integral of this larger function is going to be larger than the integral of the smaller function, okay? That was kind of redundant, but the point is that the integral is able to sort of witness the inequality here between f of x and g of x. The derivative actually is not able to see that, but the integral is. It captures it geometrically with this sort of phenomenon here. Okay, so that's pretty much it for this lecture. I didn't want to get into too many different details. A lot of theorems here, but we can you know, apply these to compute integrals and estimate them much more conveniently than you know, trying to compute integrals without them. Okay, so in the next lecture we'll talk about rules for computing antiderivatives and for actually evaluating integrals explicitly, and we'll start actually doing calculations with these sorts of things. All right, so see you all in the next lecture.